Okay, so as I mentioned, we'll be discussing about change data capture, CDC on short, and based on your comment from before the break, we can call it amazing change data capture, so we can call it ACDC. This pattern is around maintaining distributed data consistency in microservice architectures. So let's get into it. I was planning to say a few words about myself as well, but we already went to it, so I won't put too much emphasis on this. As I said, I'm Dan, product manager at Mambu for 3 payments teams right now. Also as a Mambuvian for the last 3 years, as mentioned, first as an engineer, and now I'm a product manager as well. Also regarding Mambu, as I said, we have customers on all continents except Antarctica, ranging from established banks to fintechs to lenders and even telcos who wanted to attack this banking area. We are more than 700 colleagues spread around the world in 11 different locations, but while this sounds nice, the most important for me at least is what happens here in Iași. We are more than 200 colleagues here in Iași, spread around 2 offices. Now that I'm mentioning it, it's a little bit funny with all the remote work, we're still talking about offices. But in the end, around 80% of the entire engineering organization is based here in Iași. So our colleagues are the ones building the product, running it in production, supporting everything that is related to this amazing solution that powers so many banks around the world. Let's get a little bit back to our presentation. What we'll be discussing about is some generic context around the problem, how we coordinate changes over multiple services and running them transactionally so that we maintain system consistency even though we have multiple services running with multiple data stores. Different aspects that we need to keep into consideration when preparing to go to production with such a system. What solutions are there available for us to implement it in Java? Because in the end, we're at the Codecamp with Java. And just as a short summary, we'll be looking over some general benefits and drawbacks of such pattern, and in general things to keep into consideration. So to set the context a little bit, let's talk about building reactive systems and what does it mean. Usually when you hear about reactive systems, there are a couple of properties that most of them have, and this is something we have been applying in Mambu as well when building our microservice-based capabilities. So first and foremost, it's around the synchronous communication, basically allowing us to build loosely coupled microservices really well isolated with each other and maintaining in the end dependencies to a minimum. Then we also have the failure tolerance, which is a very important property of reactive systems, because in the end it's all about this, being able to fail in a graceful manner, even though your dependencies are not running correctly or are not offering to you the functionality that you would expect, and recovering consistently. Once we get the system back to a state where it's running as before, it's important to reach also a state of consistency so we don't encounter any issues. Last but not least, it's about data separation. This allows each microservice to choose the data store which is best suited for its own purpose and its own use cases. These are some of the principles that we have been following when building our own solution around payments, and I'll be sharing with you how this looks like. So we'll be first and foremost looking at our own use case for payment processing. We would have our application split between multiple microservices, which would handle different parts of the payment execution. So we can start with the payment service. This one is the service handling most of the let's say, so business-related flows related to payments. Here, users would be able to initiate a payment. We would validate payment information, and two other details which are important for today. We are storing the payment as an aggregate root, the concept from domain-driven design. And we are also employing the event sourcing pattern. So we basically store the state as a series of replayable events, which we can then put on top of each other in order to reach the newest state from the system. So this is only the microservice which would be handling payment processing. Then we also have the account service, so basically a service holding all information related to the account of the end user, transaction history, balances, user information. This is where we would initiate specific transactions based on our needs. You can think, for example, once you initiate a payment, the same amount of money would need to be retrieved from your account as well. That's what we call a payment clearing. And last but not least, we have the payment settlement. So basically transform all the payment data that we have been building so far into a message which can be understood by different types of payment networks, by different banks around the world. So from a very high level perspective, these are the three main areas we would focus, each of them, of course, with their own database. And in order to more easily and scalably manage this flow, we would also implement the Saga pattern, where basically these microservices will never communicate directly with each other, but instead we would have an orchestrator, which based on specific parts of the process being finished, it would trigger the next one. For example, once the payment would be initiated, the payment service would trigger an event, which would then be picked up by the orchestrator, trigger the next step. Once the cleaning also was finished, we would then trigger the final step. Of course, each of these microservices would create their own transaction through their database engine in order to change the data in such way that we would see the payment outcome as we expected. What the Saga pattern means is that given that we have multiple distributed transactions, in case something goes wrong, for example, the second transaction would fail, we will need to trigger some compensation actions in order to bring back the state eventually to the latest consistent state. So in this case, instead of going forward with the flow, if the second step would fail, we would then try to compensate the original action, which would be marking the payment as failed back through the payment service. Now let's take a look a little bit more into detail regarding what has been actually happening in this microservice and how would it work. So it would be something like this. Somewhere in the repository layer, we would need to store the information related to a payment, as mentioned previously, as a collection, as a series of events, here sent as a collection. And what we would simply do is start the transaction, and then for each event, persist it in the database, and then publish the necessary message towards the message broker. Now, some of you probably already see what is wrong with this solution. It's to give you a hint around those lines. What we are basically trying to do is make transactionally two operations or multiple operations which couldn't really be executed in the transactional manner. What would happen if, for example, half of the events were processed, they were inserted in the database, but something would go wrong. The transactions would be rolled back, but all the events that have been previously published cannot really be unpublished, because publishing an event to a message broker in the end is not a transactional operation. So this would basically lead to different inconsistencies between microservices, where one would roll back the transaction and it would be like nothing has happened, but the second one would already start executing different parts of the process. Now, of course, we needed to find another way, and the solution we went is based around a specific component from the databases. It's called the transaction log. Now, of course, different database engines have different names for it. For example, Postgres calls it the write-ahead log. MySQL calls it the binary log, but for the sake of this presentation and simplicity, we'll call it transaction log in general. And what it is a simple list of all the changes that have been made durable, or in other words, all the transactions that were committed inside the database. Usually you would see such component used in recovery processes for the database. For example, if the database goes down and doesn't manage to successfully write all changes into the data store or into the file storage, it would, once it gets back up, it would simply reprocess the transaction log, see what operations have happened, and bring the data back to the most consistent state. Now, this is something we can leverage, and leveraging such pattern would be the pattern called change data capture. The idea behind it is very simple. Basically, we will need to read this transaction log and based on each entry, do a necessary action. In our case, the action which needs to be done is simply publishing a message to a message broker. But of course, depending on your use case, you might be ending up doing different kinds of operations. The reader or the process who does this, we would call it usually a transaction log processor or simply put a CDC application. Now, our solution would look something like this. Each microservice would not be responsible anymore for publishing directly events towards the message broker, but it would simply execute all operations transactionally. And once the transaction has been committed, the CDC application would pick it up and continue the process, basically triggering the necessary events. As you can see here, we have 3 different CDC instances, each of them pointed to a separate database, and this might be something we need to take a closer look later. And what do I mean by this is that there are certain aspects we will need to take into consideration when implementing such a pattern. First of all, as I said, three different databases. We should first of all look into reusability. Ideally, the way we implement this CDC application should be reusable. We should be able to point it to any database, and it should work without any further customization. But there are some other points as well. For example, observability, scalability, listener idempotency, or even some race conditions which might happen. And here I can even share a story from production where we encountered such an issue. So let's take them one by one and see what solutions we have available. Regarding reusability, there's a pattern called Transactional Outbox. And what does it mean is that basically instead of publishing changes directly to a message broker, each so-called business-related microservice, besides the business changes which we'll need to do, would also persist all the events into a specific table in the database with a very generic structure. This table would be called the Outbox table or the event table. And what would happen now is that our CDC application would, instead of listening to business-specific events tables, would be picking up changes only from the Outbox table. So as long as we maintain the same structure, we could point the exact same CDC application to any database, and it will be able to pick up and publish messages, for example, to the message broker. The structure of the table, at least in our case, would look something like this. We would have, of course, a uniquely generated primary key. We would have a timestamp related to when the event was persisted in the database. Then the interesting part would be the payload, which is a simple JSON representing the exact payload of the event that we would like to send. And depending on the message broker, if it is topic based, we can have something like a type or a topic where we can also specify where specifically we would want that event to be sent. And what does this give us is that each microservice can only do operations inside the transaction, which are safe and consistent. And the processing of this specific table would be done outside through a CDC application. Now let's talk a little bit also about idempotency. This is also an important topic. Let us take a scenario where we have three different rows inserted in the table through three different transactions. Of course, all of them would be written in the transaction log one after the other. And how would the processing look like? It would be really straightforward. The CDC application would read the entry from the transaction log, do the necessary processing, which in our case is publishing to the message broker, and then marking the position or the row as processed in order to not pick it up again if it ever needs to reprocess the file. Same would go for the second row, and same would go for the third. But what would happen now after we published all three changes, that when marking the final position, this step would fail and our CDC application would go down. Now, of course, the last position which was known to be processed is the second position. When the application would get back up and running, it would start after the second position, so we would get in the situation where the third position would be submitted twice. And this is why it's important for whatever microservices listening to these changes to make sure that each event is processed once, regardless of how many times it has been sent as a duplicate. Easiest solution to do something like this, of course, it would be through, for example, the event ID, which is uniquely generated per event, and microservices would have some sort of idempotency mechanism in order to not process events with the same ID twice. One more aspect we can also look over is observability. Of course, in the end, we want to run our service in production. It's important to know how it behaves. We can build metrics, distributed tracing, or even logging in order to understand how our application is running. We can look at things like processing speeds, throughput counts, and building alerts in order to understand if anything might go wrong. Now let's talk a little bit also about scalability and increasing throughput. The main issue here is that a database would have a single transaction log, and it's important for it to not become a bottleneck. Thinking of the situation where we would insert entries in the event table way faster than the CDC application would be able to consume them, it would be important to easily be able to scale it, and in the end to reach a solution something like this. Have three different replicas, ideally reading through three different partitions of the same table. It would be, of course, important to not process the same entries twice, and also it would make it easier to for all three replicas to read from the same table and not have three different tables for partitioning. The most straightforward solution we can come up with, it's simply partitioning based on event ID, basically generating a hash code and partitioning by the number of replicas, and then each replica would simply skip events which are not part of their own partition. As I promised earlier, I'll share a quick story of a bug we encountered in production. It was happening from time to time. That was the interesting part. It wasn't happening, it wasn't easy to reproduce. That when a specific peak load would be processed by the system, some payments would get stuck and we wouldn't have a straightforward way to understand why. Our microservices would tell us that information that was recently committed in the database was not available, but when querying for it, of course, it was there. So what can we do? The root cause is the basic way of working of the transaction log. A database engine would usually write the operation to the transaction log before actually writing it inside the file or data storage. What would happen here is that when the system would reach a certain load, the database engine would start propagating these changes towards the file storage a little bit slower than expected. So we would end up in a situation like this, where the transaction log would be correctly updated, but the data storage would not be yet updated. So, of course, we would process the row, a message broker would publish the message to the necessary service, and our service would simply want to query for the row that was just committed to the database. Since it wasn't propagated yet, of course, we would receive no result, and here would be the place where our process stopped. Yes, the simplest way to mitigate this problem is to introduce a retry policy, basically considering the fact that the information is not already there, unexpected behavior of an eventually consistent system, and set up some limits of time where we can retry this specific operation until the data is available to us. Then we would do this retry, and of course, after the database engine correctly executes the remaining of the processing on its end, we would get returned with the results that we expected. Now here we have actually two different approaches to this. Either we implement a retry policy such as this one at the service which is actually needing the row that is queried, or implementing it directly in the CDC application. Basically, as soon as it reads the entry for the transaction log, hold the process until the row is available in the database as well. You of course here have different benefits and drawbacks for each of them, and it's basically about eagerly or lazily waiting for information to be available in the system. If you do it in an eagerly manner, basically waiting for it in the transaction log processor level, the throughput might be affected, basically the end-to-end processing speed, but this would be the more consistent approach. The other approach, doing it in consumer services, to call it so, would provide better speed, but as mentioned here, you will need to take care of eventual consistency as well. We have talked so far a lot about this concept in general, about this pattern. Now let's look a little bit more under the hood, how it looks like, how we can process it in Java, and we'll start by analyzing the transaction log, a simple example from, in our case, MySQL. So in MySQL, the transaction log is stored in files, and it also offers us a quick way from the command line to access those. It looks something like this. I have added an excerpt for two different entries. The first entry, and what is most obvious here, you would see an insert in the database, where in the event table, we would add a row, and here you see the columns and the information which has been inserted for each column. There are some other pieces which are interesting here. First of all is the position inside the log of this specific entry. Then we have information like timestamp, the server ID in case our database engine runs in a clustered mode and multiple servers are writing to the same transaction log. Then we have the finish position, basically where the next entry would start. Since we're looking at the second entry, you can see here that this is actually a commit command. So it's basically a separate entry for the simple reason that inside the transaction, we might see multiple inserts or delete or update operations, which would be listed one by one inside the file. And in the end, we would have this commit, which basically tells us that all the rows until now have been committed part of this specific transaction with the transaction ID that has been assigned by the database engine. So how do we process this in Java? I will be showing you two different clients. One of them is called Maxwell's Daemon, which is a very simple, lightweight MySQL transaction log processor. It offers out-of-the-box adapters for most commonly used message brokers like Kafka, Rabbit, or AWS Kinesis. But also the nice part about it is that it is easily extensible with proprietary adapters. For example, if you want to use a different messaging system, or if you want to do another kind of operation inside the CDC application, this would, of course, allow you complete freedom. The main drawbacks is that it only supports MySQL as a target database, and also the fact that it does not offer high availability support out of the box. Most of the aspects I have shown you earlier would be something you would need to proactively introduce support for in order to be safe. I'll show you now an example of a custom producer. In our case, we would want to publish events to a different messaging system. And the idea behind it is very, very simple. We would just need to extend a specific class, an abstract producer, and implement the push method, which would basically be called for each row that has been written to the transaction log. What we do here is that we buffer all rows, part of a transaction inside in memory. And once the transaction has finally been committed, we would then process all the rows from the buffer, clear the buffer, and then mark the position as processed in order to move forward. Another tool would be Debezium. This one is a little bit more mature than Maxwell. It offers support for multiple databases out of the box. So besides MySQL, it also has Postgres or MongoDB. And again, it offers great customization support through a library which is called Debezium Embedded Engine. So basically, by introducing a simple library into your application, you are able to react to changes directly from your app. As drawbacks, it only supports Kafka by default as a message broker, so you will need to customize it for anything else. And again, it does not offer a complete high availability solution out of the box. And again, you will need to take care of the previously mentioned aspects. The code is fairly simple here as well. We would simply create an instance of a Debezium engine, point it to the correct database, and then mention the method which we use to publish events, because in our case, we would simply publish an event. But let's also open an editor and see how it actually looks like. For this demo, I have prepared a very simple application, which would be, let's say, mocking the payment service on our side. It exposes a simple API, which allows a user to, let's say, create a transfer. And this application, what it would do is basically create two different events, which would be stored in the database. And here in the repository layer, of course, you would see a very similar behavior as I have already showed you. Start a transaction, and for each event, add it to the database. And by adding it to the database, it's simply inserted into the event table. Okay, now that we have the application which produces these records, let's see how the consumer looks like, how the CDC looks like. So first of all, this is the app. It's very, very simple. You would need to provide a factory, which would create this new instance of the custom producer that we want to expose. In our case, the custom producer simply publishes messages to Kafka. This is just for an example purpose to show you how easy it is to build some custom logic behind it. So this custom producer, of course, would have a specific Kafka configuration to connect to the correct Kafka server. And inside of it, we would see a similar logic where all rows will be buffered in memory. And once we reach the commit row, we would process them, and by processing, we simply create the record in Kafka based on the topic, which is the type column, and then we have the content, which is the payload column from the event table. Once all the events from the buffer have been processed, of course, we'll clear the buffer and mark the current position as processed in order to move forward. Let me now initiate one payment in order to receive a few events in our table and show you how it actually looks like from Maxwell's perspective. So I will simply call an API. I have prepared here a simple payload. And again, once this API is called, two different events are inserted in the database. and we can take a look at them here. Let me zoom in a little bit. So this is what an entry would look like from Maxwell's perspective. First of all, we would have the database for the schema, the table, the operation. For example, we inserted this specific row, timestamp when it was inserted, transaction ID, and here it is important to notice the difference. We have the same transaction ID for both rows. This means that they were both inserted part of the same transaction, but only the second one has the commit flag true. So only after the second one, the transaction has been successfully committed. Then, of course, we have the data, and the data in our case is the exact event ID, event row. It has a unique ID, it has a creation date, it has a payload, which will be published to Kafka, and it has the topic, which, for example, is called transaction executed. Of course, I also have some Kafka command line consumers prepared here, so I can also show you how events are published in Kafka. There are two different topics, so once I reinitiate this API call, we would see that each topic would receive a new event with the exact payload that has been inserted in our outbox or our event table. This is very similar to what we have been actually implementing as a solution. We went for Maxwell, as MySQL is our database engine for now. And also due to the fact that at least initially we were using a different message broker, which was not supported by Maxwell, so we had to build our own custom producer. In the end, we migrated to Kafka, but we have maintained the custom producer. So as you can see now, we have two different types of operations: the events which are persisted in the database transactionally and consistently, and all the operations that are happening outside the transaction, basically processing each row and publishing it towards a message broker. Of course, we have taken care of all other aspects I have mentioned in this presentation previously. These are things that we encountered either before going to production or in production, and these are the things that we had to overcome, and I have already shared with you the solutions that we have taken. There are, of course, some other use cases which we can take a look at when CDC might prove useful. First of all would be audit logging. So basically, if you want to log for audit purposes any kind of change or some specific set of changes that are done in the database, it is fairly simple because this logger can be implemented completely separately from the application which is actually changing the data. So you would receive a really, achieve a really good separation of concerns. Then we have the use case of data propagation. Basically, it would be fairly easy to implement a real-time propagation between two different data stores. And the best part about it is that it would come with no noticeable impact on user performance. Again, user would notice what would happen up to the point where the transaction is committed. If anything happens after that it would not really affect the user. So in this case, it would the user doesn't even need to know that something is happening behind the scenes. And last but not least, it's also a nice pattern to use when implementing CQRS. So basically, every time a command is executed and the state of the data is changed, we can pick up those updates and read and update one or more read models based on the changes that have been happening. So some quick conclusions regarding this pattern from a high level. First of all, it promotes asynchronous processing, so it is best suited for reactive systems. Then, as you have seen, it's very easy to implement a generic solution, so that we can reuse the same logic for any database and for any application that is looking to send such messages in a, let's say, so transactional manner. And last but not least, it's completely flexible. It allows you to do any kind of processing you consider necessary, process rows one by one per batch, publish messages, do changes directly in the database, whatever you consider necessary and whatever you need for your use case, you can really make it happen. The not so nice parts or parts which would provide a little bit more work, of course, we need to maintain an extra service and we need to maintain it in production. So we need to take care of observability, availability, scalability, and all the other entities, to call them so. And then there's one more topic, which might not affect you, but in case you will ever end up in the situation, it's good to keep in mind. Currently, database engines did not, let's say so, agree on a general protocol for exposing transactional logs. So their structure and the way they work might be different from one database engine to another. So unless you use a tool such as Debezium, which offers out-of-the-box support for multiple database engines, in case you would ever need to change the data store for one of your applications, you would also need to take into consideration how to tackle this case where you would basically need to migrate the way your CDC app works as well. Before going, I also wanted to remind you to visit the Mambu virtual booth, where we have prepared a small quiz for you, and if you answer correctly, you'll have the chance to enter a raffle for some nice MAG vouchers. So thank you very much for your attention, and I'm really looking forward to your questions.
Thank you, Dan. I really enjoyed the presentation. I mean, like a very fluent story with all the issues that you encountered and the way you addressed them. I love these practical experiences.
Yep, I think this is the best way to show it in the end. Practical examples.
Yeah, absolutely. So, what happens if CDC fails? I mean, everything is event-driven. Okay, what if you want to replay things because you're missing the information? I don't know.
So, ideally, the worst thing that happens is that there might be a slight delay in the whole execution process. Once this application goes down, usually it would be brought back up to speed by the different kind of deployment managers you have. For example, you would run it in a Kubernetes cluster. So once it goes down, it would be brought back up, and then it would continue processing where it left off. Again, keeping in mind idempotency, keeping in mind that it's asynchronous, so there might be a slight delay, but in the end, the system will become eventually consistent.
Yeah, brilliant. What else do you plan in the Mambu product? Because in the last years, I've seen a lot of goodies coming.
Yeah, so during this period, what we are focusing most is actually around targeting larger and larger customers. The big fish, the large established banks with user bases of millions of people. This, of course, brings next level challenges related to performance, scalability, and everything else. So it's actually been a really nice challenge to rethink a little bit our systems and what we can do in order to make them, support these kinds of loads.
You have to be ready for the success, right?
Yep.
Absolutely. All right. Good. Any final thoughts from your side for the, I don't know, for the engineer in us, or for the Java developers,
me, right?
or for the engineer in them?
I think something that will always be applicable is try to be as curious as you can, understand how things work behind the hood, under the hood, because it will only make you better. It will only improve the way you're thinking about things. It will improve the way you're preparing solutions. Try to be as curious as possible with whatever you're working on.
Told you.
I wrote it down.
Thank you. Thank you, Dan.
Well put.
Okay.
So I think, yeah, we can, let's say, close this session with this message.
Wait. There are a couple of questions. Let me
All right.
see if I got them. So someone is asking about how to compensate actions in the callers. Not sure what that means. If you got it.
So basically how it works is that each of the microservices would of course expose the compensatory actions on their level, and it would be the responsibility of the orchestrator in case something goes wrong to know at which step of the process it stopped and trigger compensatory actions for the services that have already done their part of the execution.
Mm-hmm. When you mean orchestrator, you're referring to, I don't know, Kafka or whatever other, or
well, it's not just a message broker. It would need to be an actual orchestrator between microservice, because there is where you would usually define the whole, let's say, so processing flow. So that is the application which knows a payment would start with the initiation, would continue with the clearing, and would go to the final step. And that is the point where you can take the decision, okay, one out of 3 steps has been executed successfully. This is where I need to trigger the compensatory action.
Thank you.
All right. And another one, this one. So with CDC, of course.
So yes, both solutions offer possibility to sync or basically continue where they left off. And of course, in case they didn't left off anywhere because it's, for example, the first time they are connected to a database, they would have what is called bootstrapping, where they would reprocess all the events that are currently in the database, in order to make sure, of course, nothing would be left behind.
Brilliant. Thank you so much for this very insightful conversation, Dan.
Welcome.
All right, and yeah, see you next time. In the meantime, everybody, we take a 14 minutes break.
What?
Yeah, I'm good with numbers.
40 or 14?
14.
Okay.
14.
Good.
So you need to come back sooner.
Okay. I'll do that.
And then, yeah, we regroup with the next session.
Bye, Dan. See
Thank
you
you,
next
guys.
time.
Thank you. Bye-bye. See you.